Today we're going to be talking about the IPv6 address structure, and then we're going to move on to IPv6 network transmissions. And with that, let's go ahead and begin this session. Of course, I'm going to begin by talking about the IPv6 address structure. Now, IPv6 is the answer to the question of what do we do about running out of IPv4 addresses? Unlike IPv4, IPv6 will provide enough Internet Protocol IP addresses for the foreseeable future. Now, shortly after the creation of IPv4 and its implementation, the IANA, the organization that's tasked with assigning routable IP addresses, realized the available IPv4 address space would not be enough in very short order if nothing was done. The IANA then set about creating the replacement, and they initially started by working on IPv5. While they were working on IPv5, they found that due to the popularity of the internet, which was increasing at that point in time, that it wasn't going to be enough. So they scrapped IPv5 and began working on IPv6. Now the IANA is confident that IPv6 will function as the replacement for IPv4 for many decades to come. Why are they so confident? Well, we'll get to that here in just a moment. Now, IPv6 works at layer 3 of the OSI model, just like IPv4 does. Layer 3 of the OSI model is also known as the network layer, and its major focus is logical network and host addressing. IPv6's job is to provide logical network and host addressing to devices. IPv6 is a 128-bit binary addressing scheme as opposed to IPv4's 32 bits. The 128 bits are grouped together in sets, with each set being separated by a colon. Now each of these sets is 2 bytes long, and a byte is 8 bits. For human readability, the binary IPv6 number is converted to hexadecimal, that's base 16, with each hexadecimal number being equal to 4 bits. Now those 4 bits can actually be referred to as a nibble because it's half of a byte. An IPv6 address is 8 sets of 4 hexadecimal numbers, each being separated by a colon. That means that there are over 340 undecacillion addresses available to IPv6. That's 2 to the 128th power, which is roughly equal to 340 times 10 to the 36th power. See that number there? I'm not even going to begin to read that one to you. So now let's talk about IPv6's local address structure. For the local address, the first 64 bits on the left represent the local network, and the last 64 bits on the right always represent the host. The local address structure follows the EUI, or Extended Unique Identifier, format, specifically the EUI 64 format. For those hosts that have a 48-bit MAC address, that 48 bits is actually padded with an extra 16 bits to make it 64 bits in length. You can always tell a local address, which is also called the link local address, as it always begins with an FE80. With IPv6, every device gets both a local address and it gets a global address. Now the global address is unique. There is only one, and every device gets one. The host address is still always the last 64 bits, but every device actually gets assigned to a global network. The network portion is actually composed of a routing prefix and a subnet. This portion of the global address structure follows the classless interdomain routing, or CIDR, convention, with the number that follows the slash denoting the routing prefix. That's the part of the extremely global network that you belong to. The subnet is composed of the bits between the prefix and the EUI 64 host address. Global IPv6 addresses always begin in the range of 2000 up through 3999 in that first group of numbers on the left. Now, in most cases, the need for Dynamic Host Configuration Protocol, DHCP, has been eliminated. When implemented, IPv6 will auto-configure both the local and the global addresses that are required for their networks. When a device first comes online, it will use the Neighbor Discovery Protocol, NDP, to discover what the required network addresses are, both the local and global addresses. This allows devices to configure its own IPv6 address without an administrator's intervention. So let's talk about IPv6 notation. The 128-bit nature of IPv6 makes it cumbersome to write out, and it can take up unnecessary space. Because of this, some rules were developed to ease the burden and save space. When you're looking at a group of IPv6 numbers, any leading zeros in a set can be dropped. The thing to really remember about IPv6 is that only a single set of consecutive zeros may be replaced with the double colon. Why is that? Well, because if you could do it more than once, how would routers and other devices know how many zeros to pad in there? Even with this ability to shorten it, it's still difficult for us to remember IPv6 addresses, but it is still easier to write out, and it still conserves space within systems. Now let's move on to types of IPv6 network transmissions. And we begin with the unicast. Unicast is one-to-one communication. That is where a specific device is sending network traffic to another specific device. Unicast can occur on the local network, which remember always begins with FE80, or it can occur on the global network. Then there's multicast, which is one-to-a-few communication. With multicast, a specific device is sending network traffic to a specific group of devices that have registered to receive that traffic. Routers register to receive multicast transmissions that involve the routing protocols that they are programmed to use. With IPv6, multicast addresses always begin with an FF. Both IPv6 and IPv4 use both unicast and multicast transmissions. A unique type of transmission to IPv6 is anycast. Anycast is one to the closest communication. This is where a specific device is sending network traffic to a specific IPv6 address that has been assigned to multiple devices. The router only sends the communication to the closest one, at least from its perspective. Anycast transmission involves implementing DHCP v6. Earlier I said we really don't need to worry about DHCP anymore, but that's only partially true. While IPv6 is capable of auto-configuring its own local and global addresses, in certain situations that's not always desirable. DHCP v6 version 6 can be configured to hand out specific IPv6 addresses or duplicate IPv6 addresses when necessary. That's useful for when load balancing a network or when network redundancy has been created, or when you have a user that has a tablet, a cell phone, and a laptop, and you want to deliver the transmission to the closest device, the device that he's using at that point in time. That is where DHCP v6 comes in handy. IPv6 and IPv4 are not compatible, but we can do what's called a dual stack configuration. That's where the network and devices on the network receive both an IPv6 configuration and an IPv4 configuration. Or we can use what's called tunneling. There's 6-to-4 tunneling, which is used to encapsulate an IPv6 data packet in an IPv4 datagram, allowing that IPv6 packet to travel across or through an all IPv4 network. 6-to-4 tunneling can also be called Teredo tunneling. Now that concludes this session on the introduction to IPv6. I talked about the IPv6 address structure, and then I talked about IPv6 network transmissions.